Alright, I'm gonna do one more for today. Hopefully I can get this one, considering I did not get the last two. This is the elite code, what's it called? It's called just the daily challenge. So we've got an undirected graph consisting of n nodes labeled from 1 to n. A star graph is a graph where there is one center node and exactly n minus 1 edges that connect the center node with every other node. This is called there's a name for this. I'm gonna quickly Google this. This is called, okay, it is just called the central node, but it could also be called the cut vertex, I think. Yeah, it's the cut vertex. So you are given a 2D integer array edges where edges I equals ui vi, indicating that there is an edge between the nodes ui and vi. Return the center of the given star graph. Alright, let's get rid of the other problem and draw this one out, I think. Okay, immediately I look at this and I see the solution, but I'm going to draw it out anyway, just so I can explain it. So here we have our graph. I'm going to draw it again from this list. So we have 1, we have 2, and that represents the edge. We have 2, we have 3, that represents the edge, and then we have 4, and we have 2. So 2 is our answer because it connects, it's the center node. So we know it's a star graph, and I'm pretty sure a cool property of a star graph is that this will be the only cut vertex, which means this will be the only vertex that has edges connecting to it, if that makes sense. So like 1 and 4 can't be connected, 3 and 4 can't be connected, 1 and 3 can't be connected for it to still be a star graph. So what we can actually do here is we can just take our list of lists 1, 2, 2, 3. We can actually discard this third element because it doesn't matter. We only need 2 nodes, like 2 edges, sorry. We only need 2 edges here because if we cross this out, none of these other edges are going to be able to connect to each other. It's all going to share one common node. So we only need to compare the first 2 elements of our edge list. And in those elements, we can go, so we go for I in range 2, because again, we only need element 0, elements 1. We then go, what's it even called? Just edges. So edges for edges for edge in edges I. We can just add these edges to a list or a set. So we'll have our ls equals a set up here. ls.append edge. In here we're going to have if edge not in ls ls.append edge, else ret edge. It should actually be 4 nodes in edges I. I'm gonna try that. I don't see how this won't work, but maybe it won't work, so ls equals this for I in range 2 for node in edges I. ls.append node, but first we need to do if node not in ls. Actually, let's just go if node in ls, return node, else ls.append node. I think this works. And this is what? For I in range 2 for node in edges I, this is like probably constant time. I think this works. Let's give it a go. I hope it works. Yeah, sweet. I wonder if I can get it faster with a set, or it does that weird thing where like once you or not weird thing, but if you submit multiple times, it doesn't always work that well. But I want to try anyway. It'd be cool if a set made it a little bit quicker. 650. So this beats 70%. Let's see. A little bit quicker and better memory. Yeah, pretty happy with that one. Gonna take a screenshot. Cool.